All right, let's get started. Thanks for being here. Hope you guys are doing well. I'm going to just start off by a couple of reminders, kind of updates, reminders before we get to the review that you guys are here for. So as a reminder, this is from College Board, unacceptable things to use during the AP exam. So no communication with any family members, relatives, or friends. No internet searches. So the question is, how would they know whether you're doing internet searches? And so I don't know, but I think just to ease your, your mind, and that you're not having to worry about it, just gather all the information that you need, either in printed form or download it onto your computer, so that you're not having to worry about, wait, am I doing something that I'm not supposed to do? So if you just stay off the internet during your testing session, that'll give you peace of mind, right? That you can say, I didn't, that you're not doing anything online, and there's no possibility of you being seen as, like them catching you for doing something that they're not supposed to do. So I think that just for peace of mind, and also just to be safe, just stay off line while you're taking the exam, in terms of don't look anything up. Obviously no live online study guides. I don't think any of us are, right, we don't have anything shared in terms of Google Doc that I have with the class, so I don't think that's going to be an issue, at least with our class. But just make sure you don't do it, have any shared files with any of the students. So no online chat rooms, no forums, don't have a Zoom session with classmates while you're taking the exam, no social media. Okay, so just a couple of reminders, right? So any questions you guys have for me? Right. Yeah, feel free to ask by unmuting yourself, or you can ask in the group chat. So I just want to kind of go through again. I think, the most important thing is, you being able to go through the exam experience, regardless of how prepared you feel. The most important thing is that you're able to get into that system, and that you're able to take the photos of your work, and be able to upload it successfully. So, being able to, you have to decide, right? Do you want to use your e-ticket to log in with your phone, tablet, or laptop? All right. And, I've tried all three methods. Phone and tablet is the least cumbersome, in terms of, you have to go through a couple of devices. If you go through laptop, you have to have a phone in addition to your laptop. So having everything on one device it's just less cumbersome, right? You have to go back and forth. But I just do want to go through the steps for laptop method if you choose to use it. So this is what I end up doing. This is one of the methods that you can use. So if you want to do laptop method, obviously you have to make sure you grab your e-tickets, either from your My AP login or the email you receive from College Board. And you're going to log into your using your laptop. And when there's 5 minutes remaining, you can go ahead and start taking your photo using your phone, and make sure that you're in JPEG and not HEIC. So that's important, that you're going through your exam demo, and that you're making sure that the files that you're taking are in the correct form. So I have the directions to switch from HEIC to JPEG if you're using iPhone. And so that's here. You can go to camera, format, and switch from high efficiency to most compatible. Okay. Okay, if you're using Android, then probably have to figure out a way, making sure that you are in the correct format. So then what I also did was I made sure that my phone had Google Drive app loaded, so that I can just, open up that app, make sure that I just created a designated folder for my uploads, and I copied those photos into my Google Drive folder. And then I went back to my laptop. I found the files on Google Drive and I downloaded them onto my laptop. And then I attached a photo, one photo at a time, into my exam demo. And then I finally hit submit. So a couple of advantages and disadvantages. You have to decide for yourself which is the method you want to use. But a couple of advantages I see is, you have a bigger screen. You don't have to potentially scroll up and down just to see all the parts of the problem. That could be beneficial. You can see the timer clearly on the screen along with the problem. Sometimes if you're using a phone or a tablet, and you may not be able to see everything on the screen at once. And also, some students prefer to print out their test, and they will be allowed to do that. So it's easier to do that from a laptop. Usually it's easier to set that up. Set up printing options from your laptop. So those are some advantages that I see. Now, obvious disadvantages is cumbersome to have to go back and forth between laptop and phone and have to involve Google Drive or email or AirDrop, to transition those photo files from the phone to your laptop. And also, this could be the bigger disadvantage, is that it's just more time consuming than using a phone and tablet. However, if you went through the exam demo a couple of times, you should be pretty comfortable with it, but obviously comes with disadvantages that you have to make sure you consider. Okay. All right, so I just want to kind of point that out. So if you're here for tomorrow's last minute session, I'll probably go over this again. And just maybe I want to answer any questions that you guys do have for those of you who are trying the exam demo tomorrow. So we don't know, again, exactly what type of topics you're going to see, but seeing how other studies are going in terms of other teachers online, and seeing the pattern that we're seeing is that it's probably going to land between one of these four. These four are probably going to be the ones that have the biggest chance of showing up as a starting point. So my guess is a derivative graph and Riemann sum. However, it's easy for them to combine it into a multiple setup. Okay. But regardless, if it's just the first two, I feel like they're going to try to work in the third and fourth. So tomorrow for our review session, I'm going to do one FRQ for each, so that you can kind of see kind of the big four topics. But obviously keep in mind that they can, the reason why these four are good is because it's easy for test creators to put in all these different topics as subparts within each problem. So you may see a curve sketching, maybe as a related rates part, maybe there's a particle motion, maybe there's something involving limits continuity, maybe something involving implicit differentiation, a second derivative. And then look for the fact that they're probably going to try to work in one of the theorems. Maybe it's a mean value theorem, extreme value theorem, Rolle's, intermediate value theorem, second derivative test. So on my advice topic session that I did a couple of days ago, I kind of went through kind of these trigger words that you can look for to help you decide which method or what these test writers are trying to get you to reference. So, make sure you go through those tips of advice. Okay. All right. Any questions here? All right. Extra credit is due Monday by the end of the day. So, so if you want to turn in any extra credit, you can turn in none, you can turn in one, you can turn in multiple, you can turn in all, whatever you decide. The restriction is that I got to have it by tomorrow, Monday, end of the day, if you want to receive credit for it. Okay. For those of you who are here, can one of you confirm whether you received your e-ticket for Tuesday's AP Calc exam? You should have received it today. They say 2 days. Okay, great. So a couple people said that they received it. Okay, so double check. Okay, maybe it's stuck in your in one of the in your spam folder. But even if you don't receive the ticket, you should be able to go into your My AP login and be able to grab that. Okay, so I'm going to ask this of you tomorrow as well. That make sure you have your e-ticket. You want to make sure you have a way to get into your exam experience. Okay. All right, so let's go into mock exam 3. Okay. I think in the interest of time, again, I'm going to be kind of just going through some of the solutions, just kind of pointing out different steps. And then other parts I may work out piece by part, especially ones that maybe are more involved. I don't think you're going to see a related rates problem like this one here. But I created this mock AP exam, this particular problem, not because I think you'll see it, but just because I feel like it's easy maybe for them to insert at least one related rates into a problem. And so I figured, well, let me just put all the popular variations of related rates into one problem so that you guys can see what they look like. And if they do show up, maybe a variation, if it shows up, it'll be kind of fresh in your mind. Okay. All right, so let me read through number 1 here. So a person stands 40 feet from a point Q and watches the balloon rise vertically from point Q. Balloon rises at a constant rate of 3 feet per second. What is the rate of change in radians per second of angle theta at the instant when the when the balloon is 30 feet above the point? Let me move this a little bit so that you guys can see this a little bit more clearly here. All right, so a couple of key words here. We know this is related rates because if you see word problem format, that's a good indication, right? So if something is set up where you can visualize it, it's a word problem. It is something where there's motion involved, and when there's time is involved. Those are good indications, right? That, okay, this is a related rates problem. I'm gonna have to start off with an equation. I got to find the derivative. I have a bunch of d over dt that's going to show up all over the place. Okay. So let me walk through the steps for, well, I may work through this by hand since, or show you all the parts since related rates with trig functions tend to be, it's probably the one that we'll probably practice the least with. So we know that we have a trig equation. Anytime you see theta and there is time involved, you got to start off with a trig equation. So we have to create a trig equation that's going to relate the information that we have for our triangle. We know the person is standing 40 feet from point Q, so we know that we don't have to put a variable there. We know that's just, that person is not going to move, and this distance is going to stay the same all the way throughout this problem. Now the balloon is rising, so we want to have something involved here. So I'm going to call that y. So now using these 3 parts, we want to create an equation. We have theta. From the theta's perspective, this is opposite, this is adjacent, so we know we got to use tangent. Okay, so there's our starting point. So tangent theta equals y over 40. I know I have to find the derivative. So I'm going to rewrite this. I'm going to push that coefficient out in front. So it's easier for you to see that this is just power rule. I don't have to go through any messy thing like quotient rule here. All right, so let's find the derivative. So tangent theta becomes secant square theta, d theta dt. 1 over 40y, the 1 over 40 is a coefficient that stays, and the y becomes dy dt. Okay, so eventually we're going to have to plug everything in here. It says we're trying to find the rate of change in radians per second of angle theta. So we're trying to find d theta dt. So ultimately, this is what we're trying to target. Eventually, we want to solve for this variable here, d theta dt. Okay. So let's see what information we can gather. Okay. We know that the balloon is rising at 3 feet per second. So we know that is involving with that vertical motion. We can gather that information. dy dt is equal to 3. Okay. And now let's see, what information do we still need? If we want to find d theta dt, we need to find secant squared theta, right? We don't know what that is. But we're not going to have to figure out theta. Okay, we're going to figure out what is that entire secant of theta. So to do that, we need some information about the triangle at this moment in time. So I'm going to put this off to the side here. Okay, so let's say we have a moment in time's information. Imagine we're taking a snapshot at a specific moment in time, and that moment in time is when the balloon is 30 feet above the ground. So this is a moment in time, and we know we have a right triangle. A squared plus b squared equals c squared. We know the hypotenuse. The distance from the balloon to the person is going to be 50 feet. So from this information, we can figure out what secant of theta is, right? Secant of theta is just going to be hypotenuse over adjacent. So hypotenuse over adjacent, so 50 over 40. Which is equal to 5 over 4. So now we have a perfectly valid a numeric value to plug in for that secant theta. Careful though, this secant theta is quantity squared. So this is really secant theta parentheses squared. So when you plug that 5/4 in, make sure that you're squaring your fraction. So now I'm going to put everything in. So I have secant theta, which is 5/4 quantity squared, times d theta dt is equal to 1 over 40 times dy dt, and dy dt we found is 3. Okay, so now it's easy, right? Now we can use our calculator. We can divide this over. This is 25 over 16. We flip that over, which is 16 over 25. So this is 3 over 40 times the reciprocal of this. And that gives us 48 over 200, which is equal to, reduces to be 6 over 25. Units of measure. Obviously, you can use your calculator to do all this if you like. 6 over 25. Our theta is always going to be in terms of radians. And then the time unit here is per second. All right, any questions here? All right. Part B, I'm probably going to show the work here rather than working everything out. Pythagorean Theorem, you guys should be, for all these related race problems, this is the one that's probably that you're probably most comfortable with. So Pythagorean Theorem, bike A and B are traveling on perpendicular roads. They are both leaving the intersection, so I just drew a picture of that. How fast is the distance between them changing? So I'm trying to find this dz dt. So I know I'm starting off with x squared plus y squared equals z squared. That's going to connect all this the distances between the bikes at any moment in time. And then from here we can do we can find the derivative, and then each power rule is going to be attached to a d over dt for every variable. As the bikes are moving away from the intersection, we know these distances are going to be increasing over time. So visually, we can convince ourselves these dy dt and dx dt are going to be positive rates. Again, something to be careful about, depending on whether that distance is increasing or decreasing. Let's say both bikes are moving towards the intersection. Then we got to adjust our rates, right? So depending on how things are being played out, right? Let's say bikes A and B are traveling towards the same location. then all of a sudden, your dx dt and dy dt are going to be negative. You don't want to base your dx dt and dy dt based off of the direction, but based off of what is happening to that length, right? So you don't want to just assume, okay, if I'm going right, that must be positive. Going up must be positive. I want to think about what is happening to this length, right? So if my dx dt is 2, this distance is decreasing over time, so I need to make that a -2. And this is also decreasing, which is going to be -3. Okay, so I just want to point this out to you. Your rates are not always going to be positive, just depending on what that relation is in terms of that distance. If you can visualize that distance increasing over time, you want that rate to be positive. If you visualize that distance to be decreasing over time, then you want that rate to be negative. All right, so we gathered our information here. Pythagorean theorem will help us solve for z. Okay, now there's something additional that we got to figure out. They don't tell you, the problem doesn't tell you exactly the distance for x and y. We have to figure that ourselves, because it says how fast the distance between them changing, okay, after 5 seconds. So we got to think, all right, how far are the two bikes 5 seconds after they've left the intersection? So that means if the bikes A and B are traveling at 2 feet per second and 3 feet per second, then we can take that rate, multiply with how much time has passed, and then we can figure out the distance. So we got to use 10 and 15. Okay, so this requires a little bit of additional step for us to find those distances that we need. So once we have 10 and 15, which are the snapshot, this moment in time distance, we can figure out z by using Pythagorean theorem. And once you find your z value, we can plug everything in. So we have our x, y, we have our z. We should have 5 variables accounted for, and then the only variable that we need to look for is dz dt. And then using your calculator, you just clean that up, get it down to a numeric value, and dz dt is positive 3.606. And that positive should make sense because as x and y are getting farther away from each other, the distance between them is also increasing. Okay. All right, part C, a person 2 meters walks directly away from a street lamp 8 meters above ground. This is a very specific type of problem. I really don't, if I had to guess, I don't think this will show up, but I just want to kind of go through this with you. You know, who knows, right? So this is a very specific type of problem in terms of using similar triangles. So if you have a person walking away from a street lamp, it's always going to be set up this way, where you have the height of the person, 2 meters. You have the height of the lamp, street light. And then I assign this to be x and this to be y. And then I'm going to create a similar triangle proportion here. You see how I have a small triangle in blue and I have a large triangle in the dotted red. I'm going to set up proportions. I can say, well, the height of the small triangle is going to is proportional to the height of the large triangle, as the base of the small triangle, okay, is to the base of the large triangle. So the base of the small triangle is y. The base of the large triangle is not x times y. Okay, it's not x, it's x plus y. So we got to make sure this is where, or a lot of students, they want to do x over x plus y. Okay, but x doesn't represent the full length of the base of the small triangle. So we got to say y over x plus y. Okay, if you set up the way that I set up. Once you do that, it becomes a lot easier. Just cross multiply. Once you cross multiply, you clean up your equation, you get it down to something simple like this, and then you find the derivative. Okay. Time is again our independent variable, so 2x becomes 2 dx dt, 6y becomes 6 dy dt. And then we look to see what information we have. The person walking away, well, actually this tells us that the length is increasing at 4/9 meters per second. So just to go over everything here, dx dt is the rate at which the person is walking. Okay. Dy dt is the rate at which the length of the shadow is increasing. and then the two rates added together is going to be the rate at which the tip of the shadow is changing. So usually the problem gives you the rate at which the person is walking, but in this case, the problem gives you the rate at which the length of the shadow is increasing. So we know that's dy dt. So once we can locate and identify that 4/9 as dy dt, then we just plug that in and solve for dx dt. So when we solve for dx dt, multiply this, divide by 2, we get 4/3. So we have the rate at which person is walking, we have the rate at which the length of the shadow is increasing, and if we add the two rates together, we end up with the rate at which the tip of the shadow is changing. Okay, so just want to go over this in case it shows up. You know, it's fresh in your mind and you can go through that process. Okay, another common popular type are ones where you have to involve multiple equations. So let me go through this step by step as well. All right, beach ball is deflating at a constant rate of 10 cubic centimeters per second. Again, you know it's related rates because you have time involved. And this constant rate of cubic centimeters per second, we look at the units of measure, and units of measure really gives you an idea which variable is talking about. So cubic centimeters, you know that's volume. Per second, there must be a rate. So volume with rate, that must be dV dt. And the fact that it's deflating, that means that volume is decreasing over time. So we have to make that adjustment. That's going to be a -10. Okay. When the volume of the ball is 256 over 3 pi, so I'm going to just put that information down. What is the rate of change of the surface area? So I'm looking for ds dt. All right, so let's gather some information here. We're trying to look for ds dt. If I want to find ds dt, I have to find the equation for that. So I'm just going to gather information. We have the surface area, we have the volume information given to us. So I'm going to go ahead and just find each of their derivatives. So my v becomes dv dt, 4/3 pi stays, r cubed becomes 3r squared dr dt. And then over here I have ds dt. So s becomes ds dt, 4 pi becomes, well, stays. We bring down the 2r, so we can say 2r dr dt, which cleans it to be 8 pi r dr dt. So we have a bunch of equations, and let's see what we need, right? We're trying to find ds dt, then we need r and we need dr dt. Okay, how do we find r? We don't have a straight path to the radius, but what we do have is we do have the volume at that moment in time. So we know the volume equation connects v with r, so if I can put that 256 pi over 3 in for v, then I have a path towards solving for r. So just algebraically, we can get rid of the 3, divide by 4 pi, and take the cube root, we get r equals 4. Okay, so that's one information that we found. The other information that we need is dr dt. And since we have dv dt, we can use our dv dt equation to kind of help us work our way down to solve for dr dt. So we found r, which is also useful here. So we can plug r into our dv dt equation, and we have -10 for dv dt. We can replace these with numeric values, and now we just have to solve for dr dt. So divide this over. Now careful, when you divide this over, you notice how this pi is going to still be in the denominator. Then the tendency is we are more comfortable, or just normally we see pi with the numerator, so we just assume that it's going to be in the numerator. But here, if we divide this over, it's going to stay in the denominator. Okay. So -5/32 is the reduced value for dr dt. So now we just plug that in. Right? We have dr dt, we have r, clean that up, and we get -5. Units of measure, surface area, focus on the word area. Area is a 2-dimensional unit, so that's centimeters squared. And then time unit is seconds, so -5 centimeters squared per second. The negative should make sense to us as well because our volume is decreasing, so we expect the surface area to be decreasing as well. So this, more than the other problems, is kind of puzzle-ish because you have to work with a couple of equations, and you got to see, okay, how can I take this information and eventually get to where I need to be? So, yeah, this requires a little bit more steps, just because we have multiple parts we got to keep track of. Right? Any questions, guys? All right, number 2, this is a derivative graph with a bit of curve sketching involved. I'm looking at the f prime graph, so I like to label what I'm looking at in terms of the behavior of my original graph. So anything above the x-axis represents positive slope of the original graph. Anything on the x-axis where my original graph has slope 0. Anything below the x-axis is going to be where the slope of my original graph is negative. So it says find values where my function is increasing. So I create a slope sign line. I put my critical points, my x-intercepts on my slope sign line. So -3, 0, and 2. And then whatever sticking above the x-axis is going to be positive slope. Any portion below the x-axis is going to translate to a negative slope. So then once I have that slope sign line in front of me, then I can create my increasing statement a lot easier. So increasing from here, from -4 to -3, from -3 to 0, and then from 2 to 5 because f prime is greater than 0. Relative max is at x equals 0 because my f prime changes from positive to negative. Part C, where is the graph concave down? So I want to be able to pull concavity and point of inflection information from my derivative graph. So we know that wherever peaks and valleys are, wherever the relative max and mins are, those are going to be where my POIs are located, right? And then the slope of my f prime graph is going to translate to concavity. So concave down, concave up. Negative slope means concave down. Positive slope is concave up. Negative slope is concave down. So then we place those max and mins on as critical points on our second derivative sign line. So -3, -1, 1, and 4. Translate the positive slope to be concave up or concave down. So negative slope is concave down. Positive slope, concave up, and we should keep going down. So once you have your concavity sign line in front of you, then you have a lot easier time identifying information that you need. If it's asking for point of inflection, you see these are all changing signs. So we have 4 points of inflection. It's not what the problem is asking for, but just in case, right, a lot of information that you can gather from this concavity sign line. It's asking for concave down. So concave down, we look for our intervals of concave down, -4 to -3, -1 to 1, 4 to 5, because f double prime is decreasing, or f prime is decreasing, or we can say f double prime is less than 0. Part D, given that f of -4 is -2, we have order pairs here, 0, 5, 5, 8. Sketch a possible graph of f of x on the graph below. So this, let me go through let me do this in more detail. I have this on the key, so I'm going to go through that. How can we, maybe you're not going to have to sketch it, but let's just go through it just in case. How can we take this information, our slope concavity sign line, plus all these order pairs, and create the most accurate version based off of this information. Okay, so this is how we can start. First off, I took all the order pairs that the problem gives us. So -4, -2, 0, 5, 5, 8, and I plotted those points. Okay, so that's given, so I'm going to put that on my graph. And then I know how my graph is going to progress, right? It's going to connect through those points, and it's going to exhibit these slope behaviors. So I use dotted line just to kind of help me have a visual. I know this is not going to be the full, the perfect version of my graph, but at least I have kind of a trail to follow, right? My graph is going to rise until some point in -3. I don't know what that point is, but I know the graph is going to level off in terms of its slope for a moment. It's going to rise again. It's going to hit a max at 0 because I have that point there. It's going to fall. I don't know how far it's going to fall, but I know it's going to hit a relative min at 2, somewhere at 2, and it's going to rise again. Okay, so at least I have something to work off of. And then my next step is, okay, I have all this information from my second derivative sign line. What can I do? So I don't know. I don't really care about order pairs. I'm just going to kind of mark off my points of inflection. Okay, it doesn't matter where it is, but I'm just going to mark it off along this path that I created. So wherever my graph is at -3, I'm just going to put a dot there. -1, put a dot there. 1, put a dot there, and 4, put a dot there. So now this kind of helps give me some target points to create my curvature. Okay, so what I'm going to do is I'm just going to connect the dots with the appropriate curvature indicated by the second derivative sign line. Okay, so I know from -4 to -3, I want my graph to be concave down, so I'm going to just over exaggerate that concave down shape. Okay, so I have that here. From -3 to -1, I'm going to just connect the two dots, but I'm going to connect it in a way where it exhibits a concave up pattern. And then from -1 to 1, I'm going to connect the two dots with a concave down. Or sorry, -1 to 1, so it's going to connect all the way to here, from here to here, through 0, from this red dot to this red dot. I'm going to make it all concave down. And then from 1 to 4, I'm going to make that concave up. And then from 4 to 5, I'm going to make that concave down. So notice the dotted line doesn't give me the full picture, but it does give me some path for me to work off of, and then I can just give it more detail, and that gives me a more accurate feel based off of these two properties. Will we be asked to draw graphs? I doubt it. I doubt it. But you know, this has shown up on older FRQs, so I just figure, well, let's just cover all our bases, and if it shows up, we've gone through an example, and you can see how. And also, even if you don't have to graph it, I think this is kind of nice to really fully understand how a point of inflection looks, right? Point of inflection. All right, if you're looking at the derivative graph, right, they're showing up as max and mins, but truly on an original graph, you know where they actually belongs, right? It's really just these transition points that connects all these different curvatures together. So kind of indirectly, we're kind of also reviewing you know, the relationships between points of inflection in terms of visual relationships between points of inflection and relative max, relative min. So to answer your question, I doubt you have to draw graphs, but I still want to cover curve sketching with you. All right. And the last part is sketch a possible graph of f double prime. Okay, so f double prime means that our y-axis is going to represent something else. It's not position, it's not slope, it's now concavity. So if we want to translate this onto a second derivative graph, I'm going to label my graphs here. Anything above is going to be where concave up occurs. Anything below is where concave down occurs. Anything on the x-axis is where points of inflection occurs. So I'm going to start off by putting all the critical points onto my second derivative sign line. And then I want my graph to connect through all these points, but I want my graph to live in the location that I labeled. So from -4 to -3, my graph has to live below the x-axis. So I know I'm going to have to connect the graph from here to here. And then from -3 to -1, I want my graph to be in this positive region. So I'm going to put it up here, but it has to go through that point. So I'm going to have to find a way to make it come down. And then from -1 to 1, below the x-axis, from 1 to 4, above the x-axis, and then from 4 to 5, below the x-axis. Okay. All right, any questions there? All right, let's look at mock exam number 4. We have a function g that has a derivative g prime, where g prime is decreasing and twice differentiable. So that just means it's a smooth curve, no sharp turns. Selected values of g prime are given, and it is given that g of 1 is equal to 2. So what can we conclude using mean value theorem on the interval from 1 to 10? So from 1 to 10, mean value theorem means that we're able to guarantee a specific rate of change. So since G prime is differentiable, then we can make a claim off of mean value theorem by taking this original formula and adapt it by one derivative down. So if I take this one derivative down, I can make an adapted mean value theorem statement. G double prime of C must be equal to G prime of B minus G prime of A all over B minus A. Okay. So then if we take our endpoints, we plug in, we can guarantee a specific G double prime value. That's what we can guarantee with mean value theorem based off of what information that we do have. And we can say G prime of 1, G prime of 10 minus G prime of 1 over 10 minus 1. So this guaranteed slope, which is what we're trying to find with the slope between the endpoints, we get 0 minus 9 over 10 minus 1, which is -1. So we can guarantee that G double prime must have a value of -1 somewhere on that interval. Okay, so that's what we can guarantee with mean value theorem. All right, part B. Use left-Riemann sum with 3 subintervals to approximate the definite integral from 1 to 10 of G prime. So we're going to create values, width and height of these approximated rectangles, using areas of rectangles. So we have to find width and height. So I'm marking off the distance and representing them and subtracting them to find the width. So 3 minus 1, that's 2. 4 minus 3, that's 1. 10 minus 4, that's 6. It says left Riemann sum. So we want to, for each subinterval, we want to choose the left height. So we get 2 times 9 for the first rectangle area, 1 times 7 for the second rectangle area, and then 6 times 5 for the third rectangle area. Okay, so that gives us our approximation of 55. And then it says, is it an under approximation or over approximation? So what the problem says is that our G prime is always decreasing. So I think visually, if you can sketch a graph, visually you'll be able to convince yourself, right? If my graph is decreasing and every rectangle that I draw is the left endpoint connected to my connected to the graph, then all these rectangles is going to be obviously an over approximation, right? We have portions that are all going to stick above the curve. So we can say, because it's decreasing and it's left Riemann sum, we know our approximated value is going to be an overestimation. Okay. All right, part C. I'm sorry, yeah, part C, evaluate the definite integral from -1 to -3 of G double prime of 1 minus 3x. We know we have to go through U substitution to get this up to G prime level. So to do that, we have to go through, let the U value be what's inside the parentheses. So we let the U value be 1 minus 3x. We convert these pieces to be in terms of U. So 1 minus 3x gets replaced with parentheses. We got to find dx. So let's find the derivative. U becomes du over dx. -3x becomes -3. Cross multiply, solve for dx. We get dx equals du over -3. And now, once we have this in place, we can think of this as -1/3 integral of G double prime of U. So the method that I did was I converted the bounds, but maybe it's more straightforward for you to just convert everything back in terms of x and then just use -3, -1. So I'll have this, let me kind of work side by side with the other method that you can do. Let me see here. move these here. Oops. So G double prime is going to turn itself into G prime. And then we can convert that. Once you find the antiderivative, you can convert this back in terms of x. And then you can work in the bounds. So what you don't want to do, okay, what you don't want to do is you don't want to match this u with a -1 and -3, because this is in terms of x, that's in terms of u. So either you convert this in terms of everything in terms of u, which is what I did here, or you convert everything back in terms of x. So -3, -1. Now notice how these bounds are out of place, but it's okay because we're not reading a graph, right? We're just bringing this down. Now, if you want to adjust the bounds, you can, and then change the sign. But that's an additional step that you probably don't have to take. But if you want to read the graph, right? If the thing that you're trying to do is you're trying to pull information from a graph, then yes, then I would flip the bounds so I can read from left to right. So we can plug this in. -3 in for x, that's 1 plus 9, which is 10. Plug in -1 in for x, 1 plus 3, which is 4. So we are at the same place if we went through the other method. And then g prime of 10 is just going to be 0 using our table. And then g prime of 4 is just going to be -5 using our table. I'm sorry, just 5. And then we get the 0 will just go away. And then we have -1/3 times -5, and that gives us +5/3. G prime of 4. Yeah, 5. So this may be the more straightforward way of doing it, just get everything in terms of x. But we could also do this. We can leave it in terms of u, and then just convert these to be in terms of u, and then plug in 10 and 4. So I do want to show you, either way that you do it, you'll get the same answer. Just make sure that whatever you're dealing with, you're choosing the same variables, everything in terms of u or everything in terms of x. All right, any questions there? All right, part D. Evaluate this messy limit problem. And when you see this kind of limit problem, that should be a red flag. Okay, this is probably going to be a L'Hopital's rule problem. Okay, and for those of you who did go through this, somebody caught a mistake that I made. So the answer on my key was 1, but I adjusted it. I made a -1. So I'll go through this in detail, but I just want to let you know that I've put the corrected version on my website. And then there's also something else I need to go over with L'Hopital's rule, because recently I found out that they don't like seeing the 0/0. There's a possibility that with the grading process, they may not like this so much. Okay, so let's talk about the safe way to go about doing this so that you can ensure that you don't have to worry about losing any points for these types of problems. So what you can do is, first off, you're going to plug in. Okay, you're going to plug in, but when you plug in, we're going to have to separate these things. Okay, so let me show you how potentially they may like for you to work these types of problems. So what you're going to do is you're anticipating this to be a L'Hopital's rule problem. So you're going to do just the numerator. Okay, so we're going to separate, make just the numerator, get see what that result is. Okay, so plug 1 in for G prime. We get 9 minus G prime, which is, our G prime is just going to be 9. So that's going to be e to the 0, which is 1, 2 minus 2, which is 0. Okay, we'll set that off to the side, and then we'll do the limit as x approaches 1 for the denominator, but we're going to write it out as its own thing. Okay, so plug 1 in, we get G prime of 4 minus 5. You look at our table, G prime of 4 is 5, so 5 minus 5 is 0. All right. You're not going to say 0 over 0. Okay, you're going to look at this and say, okay, that's obviously going to be 0 over 0. You're going to say that in your head, but you're not going to write it down. And then your next thing you're going to say is, you're going to say by L'Hopital's rule. Nowhere are you going to do 0 over 0. You're just going to find them separately. And then from here, you're going to say by L'Hopital's rule. And you're going to write out the entire problem. And then you're going to say equal to. Now we're going to push it through the derivative step. So the rule for e to the u is e to the u times u prime. And then the derivative for the 9 minus g prime is negative g double prime. So this is where I made my mistake on the original version. I just put g double prime. I didn't carry this negative over. And then negative 2 goes away. So that's it for the numerator. For the denominator, I'm sorry, this should be just g prime, right? I looked at, so g prime becomes g double prime of 4x times 4. There's a chain rule going on here, right? The derivative for g prime is g double prime, and then 4x becomes 4, and then negative 5 goes to 0. So now we can plug 1 into all the x's. And then we're just continuing through and get it down to a numeric answer. So g prime of 1 is just going to be 9. E to the 9 minus 9 is 0. E to the 0 is 1. So we get 2 times negative 4, which is negative 8. Denominator g double prime is going to be 2. So 2 times 4 is 8 equals to negative 1. So nowhere along this step are you doing anything with 0 over 0. So that's the safest way to go about doing it. Okay, you're just going to kind of have it maybe in the back of your mind, but you're just going to do this separately. So this is the safe way of doing it, where so you don't potentially have them complain and have them take a point off because they see that 0 over 0. Okay. Any questions there? Okay. For part E, we have a function defined by w of x, 3x squared and g prime. We're asked to find the derivative. Hopefully we can recognize this as product rule. But then within product rule, we got to deal with this. So there's another chain rule going on inside of it. So let me go through the steps here. We have f prime g plus f g prime. So when we get to g prime, there's an outside and inside portion. So g prime becomes g double prime, and then 2x becomes 2. So we got to make sure we handle that chain rule portion within this product rule problem. Okay, so once you're here, it becomes a lot easier. Just plug 2 in for all the x's, and then look at your table to revert back to a numeric value, and then get it down to your answer there. All right, any questions there? Okay, because of time, I was initially gonna work this out by hand, but I'll just kind of go through step by step, and hopefully we've done enough practice over the course from when we did Unit 6 that you understand all these steps involved. Okay, but for part F, it says, given the differential equation, we're gonna find the particular solution. So here's my original equation written out. Okay. So my first step is I wanna try to get my everything up in the numerator. So cross multiply, I'll move the dx over to the right side. So now everything is nicely sitting up in the numerator portion. I look at my problem and I say, is there anything out of place? I want my y's on the left, I want my x's on the right, so I'm going to divide this parentheses over to the left. Now I have nice clean separation, y's on the left, x's on the right. And now I know I have to go through u substitution here. So I let the u value be the 1 minus 2y. So I make my substitution here. I know my u value is 1 minus 2y. I also want to replace the dy in terms of u. So careful here. The derivative is going to produce a -2. So we've got to keep track of that -2, du over -2. So we replace the denominator with u, replace the numerator with du over -2. We push that -1/2 out in front. And notice that we don't bring the u up to the top because this is not going to be a power rule. This is going to be natural log, right? But if it's u to any other power, then we got to force it up, change the exponent to be negative, and then go through power rule, right? So everything is set up nicely for us to apply our antiderivative. This is natural log, and this just becomes g prime, right? G double prime, we just make it move up one level. So here's my antiderivative, my cleaned up version after I replaced the u back in terms of y, or back in terms of the original variable. So now I'm ready to find my c value. I'm going to take 1, put it in for x, take 0, put it in for y. So 1 minus 2, 1 minus 0, natural log of 1 is 0, g double prime of 1 is equal to 4, based off of our table above. Solve for c, we get -4. Once we solve for c, we're going to update our c value with -4, and then try to algebraically clean up this mess. So once I insert, replace c with -4, now I'm going to solve for y. So to solve for y, I'm going to have to plug in 3 in for x. Let's see here. Oh, it says we want to use this expression to find k of 3. Okay, so from here, I'm just going to try to work towards solving for k of 3. So replace x with 3. And then I can bring this back in terms of my value. G double prime of 3 is equal to 1. That's off the table. And then clean this up. Once I have it cleaned up, well, relatively cleaned up, there's no other variable besides x and y. And now I'm going to just multiply both sides by -2 to get that, eventually get that y by itself. Raise both sides with base e. And then I can solve for y. So I'm going to move the -2 over to the right side, move the e to the 6 over to the left, and then divide by 2. So there's my K of 3. I plugged it in a little early, but that allowed me to just solve for y. And when I solve for y, I'm getting to the numeric value because I've already replaced x with 3. Okay. Okay, question here. Can you go over why you use G prime, double prime instead of G prime? Okay, let me see if this answers your question. The reason why we use, oh, wait a second. Yeah, I made a mistake here. Let's see, G prime. Yeah, so this should have been G prime. Okay, so sorry about that. Let me. Yeah, that's going to throw things off there. So let me correct this mistake, and then I will upload it. I'll put it next to exam 4, and I'll mark it off. Okay, so let me make that. I don't want to work that out here, but I will make that change. So yes, that is something that I did not transfer this correctly. This G prime needs to be G prime here. So I think I was looking over here and I made that mistake. So everything should be G prime, and that's going to throw off a bunch of these numbers here. Okay, thanks for catching that, Gracie. And I will update this on the key so that you guys can see the corrected work. Okay, so that's something I need to do tonight. Okay, but hopefully all the other process feels right. I just made that mistake, and that's going to throw off a lot of our answers. Okay.
Mr. Yang, it just changes the e to the power 6 into e to the power -6. That's all it does.
Oh, really? Hold on. Say it again.
It changes the e to the power 6 into e to the power -6. That's all it does.
Okay. Okay. So thanks for that. But either way, I'll go through this later and do any corrections that I need to correct. Okay. Thanks. So it looks like just a minor change, but I'll go back and give you guys a better update, corrected version of this. Okay. Let me quickly go over this last problem. I don't want to hold you guys too much longer. So this last one here, find the x-coordinate of each point of inflection. We have to understand that whenever you see this notation, just understand that this is really just telling you that this f is at the h prime level. Okay, we're dealing with the h prime graph, so we're going to mark it off. Like I said, we're seeing a derivative graph. So anything above the x-axis is positive slope. Anything below is negative slope here as well. So part A, find the coordinate of each point of inflection. Peaks and valleys are going to translate to be points of inflection. So that's a point of inflection there, point of inflection here, point of inflection at 1. Right? So -2, 0, and 1, since that's where my h double prime changes signs. For part B, find the maximum value of h. So this would be an indication that we have to apply extreme value theorem. So with extreme value theorem, we have to identify endpoints and critical points. Now, critical points are not points of inflection. Okay, so we're not going to use, well, this is a carryover here, but just I want to make sure that for extreme value theorem, you're not going to consider points of inflection. You're just going to consider critical points and endpoints. So in this case, we only need to test endpoints of -4 and 3, and then critical points of -1 and 1. Okay. So now we just have to plug it into our formula, which is here. And then we're going to read the graph. So h of -4 is a definite integral from -4 to -1. But this is where I like to change my bounds because I don't like to read from right to left. So I'm going to flip the bounds, make my lower bound be my smaller value, and then flip that sign. So then I want to total the region from -4 to -1. And what I did was beforehand, I identified all these geometric shapes, and I found the area of each region. So this may be a cumbersome looking region, but I split up into a triangle and rectangle, and that makes it a little bit easier to figure out. So that's 2, 1/2 base times height. This is pi r squared over 2, that's semicircle. And then both of these are negative because these are below the x-axis. So if I want to total from -1 to 4, 3/2 minus pi over 2, -4 to -1, my bad, -4, -1. So just this region here, right? So 2 plus 2 plus 3/2, and that gives me 5.5. But because I flipped the bounds, I got to change this positive value to a negative value, so -5.5. Okay, h of -1. The nice thing here is when I put that upper bound, replace that x with -1, my bounds are matching. So if the bounds are matching, your definite integral is always 0. h of 3 from -1 to 3. So -1 to 3, it's just going to be negative pi over 2 minus 1. And that's going to roughly be around -2.5. So comparing all these three values, the absolute max is going to have to be 0. Find h double prime of 2. So h double prime of 2, I need to find h double prime of x. So since my h prime is f of x, I'm just going to move everything down. So h double prime is just going to be f prime. And f prime of 2 is just going to be the slope of the f graph at 2. So the slope of the f graph at 2, that's obviously a line that we can just do rise over run. So down 1 over 2. So -1/2. Okay. Part D here. Let the function be defined below. We have a continuous function. Is the function continuous at x equals 1? Show the work that leads to your answer. So if we want to show continuity, we have to go through continuity conditions. So does a point exist? Does a limit exist? And then finally, does the point sit where the limit sits? So we know our c value is going to be 1. So I'm going to plug 1 into the first piecewise because I see a less than or equal to there. So that's f of 1 plus 1, which is 0 plus 1, which is 1. And then notice that if I want to do a limit, I can't just do one limit statement because I have piecewise on either side of 1. So I'll do a limit from the left side of 1 and limit from the right side of 1. Now, when you do limit statements where you have one-side limit, don't overcomplicate things. You're just going to plug in that whole number. No need for decimals. Don't do anything different. Just plug 1 in and see what you get. So in this case, f of 1, we look at our order pair. F of 1 is just going to be 0. F of 3 is just going to be -1. And we see that there is a mismatch, right? The limit is not going to exist because the left and the right side are not in agreement. So we can stop there and say our function is not continuous since we have a non-removable discontinuity, and there's no need to look at that third condition. We already know it failed that second condition. Okay, last part here. Between -4 and 3, a particle moves along the x-axis. The velocity is represented by the equation of v of t equals f of t. Find the acceleration at t equals 5/2. Okay. So since our velocity is equal to f of t, then we know a of t is just going to be f prime, right? We're just taking the velocity and moving it down, both v of t and f of t, moving it down 1 degree or one derivative. So the derivative a of 5/2 is just going to be the slope of the f graph at 5/2, and the slope of the f graphs at 5/2, that's 2.5. That's going to be just along this line, and this line is going to hold the same slope all the way through, so -1/2. So now that we know that acceleration is negative, okay, the question is asking, is the velocity increasing or decreasing? Now, I purposely use this wording because I want us to be able to recognize this as different than speed increasing, decreasing. So velocity increasing, decreasing, we don't touch the velocity. In fact, this is not the same thing as saying, is the velocity positive or negative? This is the word increase decrease is now going to change this velocity to now be an acceleration information. So whenever you see velocity increase decrease, it's just a complicated way of saying is acceleration positive or negative. So in this case, because our acceleration is negative, our velocity is decreasing. Okay. Now, what if the problem had said is the speed increasing or decreasing? Then we compare signs between velocity and acceleration. Okay. So in this case, if the problem said that our velocity at 5/2, right, if this is the velocity graph, that velocity at 5/2 is obviously negative. So velocity is negative, acceleration is also negative, and because they have the same signs, we can say our speed is increasing. Okay. But if one is positive and the other is negative, then we can say that speed is decreasing. So I purposely wanted to put this in the problem so that we can be reminded that, you know, just a slight change in wording is going to affect how we approach the problem and also affect how we interpret our problem as well. Okay, any questions? Just as a final reminder, tomorrow at 7 o'clock, I'll be going over these FRQs. So if you have time, feel free to work through them ahead of time. And then also I added part 2 and part 3, just more problems for you to look at in case you just want to look at more problems. And so any questions that you guys have for me? All right, thanks for sticking around. I hope to see you guys tomorrow to do our last final session, and then we can do over any reminders that I want to go through with you. But hope you guys have a good evening, and I'll see you tomorrow.